today's class, let us look at two theorems. So that is called the Fatto's lemma and monotone convergence theorem. So for a sequence of measurable function, we have seen the bounded convergence theorem. Bounded convergence theorem states that if we have a sequence Fn of measurable functions defined on a measurable set E with finite measure, then if limit n tends to infinity, Fn is equal to f of x, then integral over E f will be equal to limit n tends to infinity, integral over E Fn. So we have a sequence of bounded measurable functions, and we have limit n tends to infinity, Fn equal to f. Then the bounded convergence theorem states that integral over E f will be limit n tends to infinity, integral over E Fn. So we'll see similar theorem again for sequence of non-negative measurable function. So the first theorem is Fatto's lemma. So if sequence Fn is a sequence of non-negative measurable functions, and if Fn converges to f almost everywhere on a set E, then we'll show that integral over E f is less than or equal to limit inferior integral over E Fn. So we have a sequence of non-negative measurable functions. So bounded convergence theorem, we had a sequence of bounded measurable functions. So here you have a sequence of non-negative measurable function. So non-negative measurable function the integrals are noikkondirunnu. So we have functions of that form, and you are given that limit Fn is equal to f almost everywhere on the set E, and then we need to show that integral over E f is less than or equal to limit inferior integral over E Fn. So we are given that Fn converges to f almost everywhere. So without loss of generality, we will assume that the convergence is everywhere. Okay, അപ്പോൾ നമുക്ക് prove ചെയ്യേണ്ട integral over E f is less than or equal to limit inferior integral over E Fn. Now as we know, the integral over set of measure 0 will be equal to 0. So we know that Fn converges to f almost everywhere. അതായത് almost everywhere in the set E, Fn converges to f. So we need to show that this holds for entire E. So now for a measure of for a set of measure 0, both the integral will vanish. So we can assume that Fn converges to f on the entire set E. So wherever it does not converge, that will be set of measure 0. So the integral over that set will be equal to 0. So without loss of generality, we may assume that convergence is everywhere. So this is because the integrals over set of measure 0 will be 0. Now to define the integral of a non-negative function, we need bounded measurable function h such that h is less than or equal to f. So for defining the integral over E f, we need bounded measurable function of this form. So let h be a bounded measurable function which is not greater than f. So we have h less than or equal to f, and h is such that it vanishes outside a set E dash of finite measure. And now let us define a sequence of function hn by hn equal to minimum of h fn of x. So hn ingane define cheya sequence of function. So we can see that hn ennu parayunnathu minimum of h of x and f of x aanu. ഇനി h of x എന്ന് പറയുന്നത് bounded measurable function ആണ്. So hn will be the minimum of this two. അപ്പോൾ ഏത് വാല്യൂ ആണോ ചെറുത് വരുന്നത് എച്ചിന്റെ വാല്യൂ നമുക്കറിയാം. എച്ചിന്റെ വാല്യൂ ബൗണ്ടഡ് ആയതുകൊണ്ട് അപ്പർ ബൗണ്ടും ലോവർ ബൗണ്ടും ഉണ്ടാവും. സോ therefore the value of hn will be lying between that upper bound and lower bound. അപ്പോൾ h of x ബൗണ്ടഡ് ആയതുകൊണ്ട് hn-നും അതേ ബൗണ്ട്സ് തന്നെയായിരിക്കും ഉണ്ടാവുന്നത്. സോ the bounds will be that or maybe less than that. So anyway, hn will be a bounded function since h of x is bounded and it will vanish outside e dash. കാരണം h നമ്മൾ എടുത്തിരിക്കുന്ന h vanish outside e dash ആണ്. അപ്പം minimum ആണ് again നമ്മൾ എടുക്കണം. അതുകൊണ്ട് again hn also will vanish outside e. Now consider limit n tends to infinity hn of x. So we have defined hn of x to be minimum of f of x and minimum of fn of x and h of x. അപ്പോൾ fn നമുക്ക് തന്നിരിക്കുന്ന സീക്വൻസ് ആണ്. h നമ്മൾ എടുത്ത bounded function such that it is not greater than f. Okay, so when you take the limit, so that will be minimum. ഇനി fn ന്റെ ലിമിറ്റ്, so limit n tends to infinity, fn of x will be equal to f of x. So when you apply the limit, so limit ഈ function apply ചെയ്യുമ്പോൾ that will become f of x. So we are going to get minimum of f of x, h of x. Now we have taken h such that h is not greater than f. So h less than or equal to f ആയിരിക്കും. So therefore the minimum value will be equal to h of x. So therefore hn is a sequence of bounded measurable function such that limit n tends to infinity, hn is equal to h. അപ്പോൾ നമുക്കൊരു sequence hn ഉണ്ട് and limit n tends to infinity, hn is equal to h, and the sequence hn is a sequence of bounded measurable function. Okay, അപ്പോൾ ഇതാണ് നമുക്ക് bounded convergence theorem നമുക്ക് വേണ്ട. bounded convergence theorem നമ്മൾ ആദ്യം പറഞ്ഞു, we have a sequence of bounded measurable function and point wise convergent ആണെങ്കിൽ then integral over e f will be equal to the limit. അപ്പോൾ here integral over h will be equal to limit n tends to infinity, integral over e hn, and now here we have defined the function h on e dash. So e dash is a set of finite measure and e dash is a subset of the set e. So by bounded convergence theorem we'll get this. So integral e dash h will be equal to limit integral e dash hn. Our aim is to show that നമുക്ക് പ്രൂവ് ചെയ്യേണ്ടതാണ് integral over e f that is less than or equal to limit inferior integral over e h. Okay, അപ്പോൾ നമുക്ക് fn ഉം f ഉം നമുക്ക് കൊണ്ടുവരണം. We have integral over e dash h equal to limit integral over e dash hn. We have defined hn to be minimum of fn and h. So this will give hn less than or equal to fn. So we will use this inequality to bring fn. അപ്പോൾ ഇവിടെ നമ്മൾ ഒരു inequality form ചെയ്യും. Okay, so let us see how do we get that. Now let us start with integral over e h. Okay. So we have hn converging to h of x for each x in e dash. Okay, so for each x in e dash, so in e dash hn will converge to h. Now let us consider of e dash എന്ന് പറയുന്നത് e യുടെ subset ആണ്. So e dash is a set of finite measure and outside e dash the measure will be equal to 0. So integral over e h will be equal to integral over e E എന്ന് പറയുന്നത് E dash union E minus E dash ആയിരിക്കും. ഇനി E minus E dash എന്ന് പറയുന്നത് that will be a set of measure 0. So on a set of measure 0, the integral value will be equal to 0. The integral over E, H will be equal to integral over E dash H. ഇനി Hn is converging to H of X in E dash. അപ്പോൾ ഇവിടെ bounded convergence theorem വെച്ചിട്ട് integral over E dash H will be equal to limit integral over E dash Hn. ഇനി all the Hns are less than or equal to Fn. So this will be less than or equal to limit inferior of integral Fn. So this is because Hn is less than or equal to Fn. So we will get integral over E less than or equal to limit inferior integral over E Fn. For completing our theorem, we need integral over E F on the left side. അപ്പോൾ ഇവിടെ ഇത് ഏതൊരു arbitrary H നും ഇത് true ആയിരിക്കും. So it will be true for the supremum also. So taking supremum on the left side over H, so we will get supremum over H is such that H less than or equal to F, then integral over E H, that will be less than or equal to limit inferior integral over E Fn. So this will be, by definition, this is integral over E F, so that will give integral over E F less than or equal to limit inferior integral over E Fn. So that completes the proof of the Fatou's lemma. So we will get integral over E F less than or equal to limit inferior integral over E Fn. Now the next theorem is the monotone convergence theorem. In monotone convergence theorem, we have a sequence of non-negative functions which are increasing, monotone increasing ആയിരിക്കും. Then if Fn F is equal to limit Fn almost everywhere, then we'll show that integral F will be equal to limit integral Fn. So that is the monotone convergence theorem. So we are given an increasing sequence of non-negative measurable functions such that Fn converges to F almost everywhere. Then we show these are equal. Now the Fatou's lemma will hold for sequence of non-negative measurable functions. So here again the sequence is non-negative measurable. So by Fatou's lemma, integral over F will be less than or equal to limit inferior Fn. ഇനി നമ്മുടെ സീക്വൻസ് Fn എന്ന് പറയുന്നത് increasing ആയതുകൊണ്ട് so for each n, Fn will be less than or equal to Fn. So if you have an increasing sequence, so if it converges, it will converge to the upper boundലേക്ക് ആയിരിക്കും converge ചെയ്യുന്നത്. So Fn will be less than or equal to F. So therefore integral Fn, for by the property of non-negative measurable functions നമ്മൾ yesterday ചെയ്തതാണ്. If Fn less than or equal to F, then integral Fn will be less than or equal to F. Now this must hold for all Fn, so it must hold for the limit superior also. So ഇതിന്റെ supremum value നെ ഇത് hold ചെയ്യണം. So therefore limit superior integral Fn will be less than or equal to integral F. But by the property of limit inferior and limit superior, for limit inferior will be always less than or equal to limit superior. അപ്പോൾ നമുക്ക് ഇവിടെ കിട്ടിയിരിക്കുന്നത്, നമ്മൾക്ക് കിട്ടിയ റിസൾട്ട് കമ്പൈൻ ചെയ്യുമ്പോൾ നമുക്ക് ഇത് കിട്ടി, ഈ ഒരു റിസൾട്ട് കിട്ടി, ഈ റിസൾട്ടും കിട്ടി. സോ we'll have limit inferior integral Fn less than or equal to integral F less than or equal to limit inferior integral